In this video, we're going to learn about something called Fermat prime numbers. Now, if you recall in our previous video, we asked the question, are all regular n-gons, n greater than 3, of course, are they all constructible with only Euclidean tools, which means a compass and a straight edge? Now let's review what that means. Regular n-gons, n is the number of sides, so it has to be at least 3. A three-gon is a triangle. A regular three-gon is an equilateral triangle. Regular just means all the sides are the same lengths. So for which n's would it be true? Well, we don't know exactly, but we do know that the answer is no. You cannot construct with Euclidean tools every n-gon. I know you can do a three-gon. We did that in the earlier video. That's an equilateral triangle. We did a four-gon, which is a square. And many others can be done as well, but not all of them can. So which ones can? Before we get into that, and we'll get into that in the next video, we need to learn what Fermat prime numbers are. So let's start off with the definition. The numbers f sub m, and we're defining fm to be 2 raised to the power of 2 to the m plus 1. For all m in the natural numbers, and let me make one correction to that. I'm going to say for all m greater than or equal to 0. We're going to include 0 in this. Okay, so all numbers of that form are called Fermat numbers. And we'll write out the first or several of them in just a minute. So where does that come from? Fermat comes from Pierre de Fermat. He conjectured in around 1640 that all of these numbers, f0, f1, f2, f3, defined using this formula, every one of them is prime for all m greater than or equal to 0. So let's look at the first few of these Fermat numbers. Let's first look at f0. Well, m is a 0, so it's going to be 2 to the what power? 2 to the 0. That's 2 to the 1 power, which is 2 to the 0 is 1, right? 2 to the 1 is 2 plus 1, and that gives us 3. Then this is 2 to what power? 2 to the 1 power. So that's 2 to the 2, which is 4, plus 1. That's a 5. F2 is 2 to the 2 squared power, 2 to the 4th power. 16 plus 1 is 17. F3 is 2 to the 3rd is 8. 2 to the 8th plus 1, that's 256 plus 1, that's 257. F4 is 2 to the 4th, which is 2 to the 16th plus 1, that's 65, 536 plus 1. 65, 537. Oops, 65, 537. I didn't want that comma there. 65, 537. Well, it turns out that all of these numbers, f0 through f4, are prime. But when we get to f5, look at this number. It's a huge number. 2 to the 5th, well, that'd be 2 to the 32 power plus 1, is 4,294,967,297. Well, back in the 1600s, this was a very difficult number to factor. So probably hundreds of years later, they determined that that number is not prime. It can be factored into 641 times 6,700,417. So this one is obviously not prime, so it would be composite. So this conjecture from 1640, where Pierre de Fermat thought, he believed that Fm would be prime F0, F1, F2, F3, F4, F5, F6 forever. Well, that's not the case at all. So we can state that that conjecture is false. And much more work has been done on this conjecture. So true or false? All Fermat numbers are prime numbers. Well, of course, that's false. We just proved it. We showed that F5 is not a prime number. It's composite. And it turns out that so is F6 and F7. The only Fermat numbers, I scratched this out. I didn't want to say Fermat primes here. The only Fermat numbers that are known to be prime, we would call those Fermat primes, are exactly these four. F0 through, 5. F0 through F4 above. They are the only ones known to be prime. The next 28 Fermat numbers, F5 through F32, and maybe more, are known to be composite. And it turns out that in all the work that's been done up to this point, not a single other prime number has been found in the Fermat numbers. Only F0 through F4. You ought to Google that just to get the latest updates to see if anything new has been determined. Many believe that Fm is composite, not prime, for all of the rest of them. F5, F6, F7, F8, ... Okay, so that's Fermat numbers, and we've also defined the first 5 of them are called Fermat primes.